In any engineering or physics problem, there is a perfect mathematical reality. We represent this exact solution, which we will call U-exact, as a complex curve plotted along a spatial domain. Because calculating this exact curve is usually impossible, we introduce an approximation curve, denoted as psi of x. It follows the general trend of the true solution, but inherently deviates from it. If we measure the physical distance between our approximation and the exact solution, we capture the local error. When we extract that gap and plot it independently, we get a new function called the residue, or r of x. Look at the behavior of this residue. As our approximation overshoots and undershoots the true target, the residue curve weaves above and dips below the zero axis across the spatial domain. If this residue were perfectly flat at zero everywhere along the axis, our approximation would actually be the exact solution. For numerical methods, generating an approximation without any local error is mathematically impossible. To build this approximation, we rely on a series expansion equation. We define psi of x as the sum of known trial functions multiplied by unknown coefficients. Those coefficients, the a sub I terms, are the blank spaces in our mathematical model. They are the variables we need to solve for. The specific numerical values we assign to these coefficients dictate the final shape of our approximation curve and therefore determines its overall accuracy. No matter what values we eventually calculate for these coefficients, we must accept that there will always be pockets of positive and negative error remaining in the domain. Our objective is to construct a system that balances these positive and negative regions against each other. By forcing the average of the total error to zero, we lock down the correct values for those unknown coefficients. The most intuitive way to balance this error is to integrate the residue across the entire domain and set the result equal to zero. This equation represents the raw integral of the residue function, r of x, set to zero. By evaluating this integral, we sum the area under the curve. The positive arrow peaks mathematically cancel out the negative error valleys, resulting in a net zero total. But executing this integration yields exactly one broad algebraic equation. Recall that our series approximation relies on multiple unknown variables, ranging from a1 up to an. We now have exactly one equation on the left, pitted against an arbitrary number of unknown variables on the right. This creates a structural deficit, known in mathematics as an underdetermined system. You cannot solve for n distinct variables using only a single constraint. The algebra simply will not close. Relying purely on the raw residue integral fails because it lacks the mathematical dimensionality required to calculate every coefficient and define the exact shape of our approximation. To solve this dimensional mismatch, we inject a new mathematical tool into the process, an arbitrary weighting function, denoted as w of x. Look at the modified equation. We multiply the residue by this weighting function before we integrate. Applying this multiplier warps the area above the curve, altering the balance of positive and negative regions and changing the resulting algebraic equation. These weighting functions do not need to be complex mathematical structures. Standard polynomial terms are highly effective. For our first iteration, we set the weight to 1. Multiplying it against the residue curve leaves the shape unchanged, and integrating it gives us our first constraint equation. For the second iteration, we use a different weight, setting w2 to x. Multiplying the residue by x amplifies the curve as it moves along the axis. Integrating this new warped shape generates a second distinct equation. We do this again, setting w3 to x squared. The area warps further, yielding a third unique equation. By repeating this process n times using n distinct weighting functions, we successfully generate the n equations required to match our unknown variables. We now have a complete array of weighting functions, ranging from w1 to wn. There is a strict constraint on this list. Every function we select must be linearly independent from the rest. If one function is merely a scalar multiple of another, for example, if w3 is just 2 times w1, the resulting integral produces a redundant equation that provides no new mathematical information. Using linearly dependent weights will collapse the calculation, resulting in a singular, unsolvable system and destroying the entire method. When chosen correctly, linearly independent weighting functions act as mathematical levers. They allow engineers to extract exactly n unique, valid constraints from a single spatial domain. We have now accumulated a complete mathematical system, a stack of n unique integral equations, each set to 0. These equations are bounded by the physical limits of our domain. The definite integrals evaluate the functions of x precisely across those boundaries. Because we evaluate across strict numerical limits, the integration entirely consumes the spatial x variables. As the calculus resolves, the complex functional curves collapse down into static, constant scalar numbers that sit beside our unknown coefficients. These resulting constants naturally arrange themselves into standard linear algebra format, an A matrix multiplied by an x vector set equal to a b vector. Look at the center of this matrix. The unknown x vector cleanly isolates our target coefficients, a1 through an. We bypassed the dimensional roadblock. By utilizing weighting functions, we constructed a robust n-by-n system of linear equations. Computationally solving this final linear system yields the exact numerical values for every coefficient, locking our approximation into its final shape. Arriving at this solvable algebraic matrix represents the successful completion of the weighted residual method's primary objective. The weighted residual method uses linearly independent weights to translate an intractable continuous calculus problem into a discrete, computationally solvable linear algebra problem.